Okay, welcome to EP1027, and this is a course on Maxwell's equations and electromagnetic waves. I am your instructor. My name is Shubho Roy, and at the bottom of the screen, you'll be able to see my email information and my office hours. Office hours for this course will be held over Skype. My Skype user ID is my first name and my last name together, all together in lowercase, Shubho Roy. Um, or by Hangouts, for which case you don't need a separate ID. This is my institute ID will be enough. So these can be conducted via appointment. I'm not giving any particular set of time because my schedule is a bit up in the air right now. So just send me an email that I want to talk over Skype because I have some queries and I'll be able to respond. Um, Otherwise, you can just email in your query and I will try my best to respond to your queries via email. So that concludes the information about the office hours and email. So let me begin by noting down the references, the literature which I will from time to time follow, but not in a linear fashion. So the main reference for this course is this textbook by Griffiths, which is the standard in most of undergraduate courses at the freshman or sophomore level. Apart from that, I would also recommend highly with the book by Ed Purcell, who happens to be Griffiths' teacher. He also has a remarkable book titled Electricity and Magnetism, and this is a part of the Berkeley volume of physics courses, which is for the undergraduate. Again, at the freshman or sophomore level, I don't think it is much more advanced than that. These are comparable, but they're completely different. Purcell has a much more physical insight. Griffiths, on the other hand, has an interesting mix of physics as well as mathematical approach. And then there's a book which is people are saying the reviews are very good, and they're saying it's like a competitor to Griffiths. It is as good as that. This is the book by Zangwill. It's called Modern Electrodynamics. I haven't looked it up, but the reviews are good and the feedback is good, so it must be good as well. Then there's the fourth one on the list, Ohanian's Classical Electrodynamics. Again, it's a very good book. This book I've read, not entirely, but sections of it, and it looks a very nice read. I would say, to choose your pick. These first four reference items, I have put it on a Google Drive, which I intend to share with the class. So you can look on the references folder, and you should be able to find these references. Please look them up, study them. The fifth one, another popular reference, which I've never read, although it was, I don't know why I've never tried it as an undergrad. But this is also a popular book. The book by Wrights, Milford, and Christie, Foundations of Electromagnetic Theory. You're welcome to go and take a look at it. And then for problems, I would recommend the Schramm series' book, Outline of Electromagnetics. There is a great thing about Schramm series, it has a lot of practice problems, so you can test out your knowledge or how well have you mastered the material. By way of general references, of course, Feynman Lectures Volume 2. Feynman Lectures, as most of you know or are familiar with, is a great resource for the undergraduate for general physics. It was delivered and written by Richard Feynman, one of the best physicists of all times, a Nobel laureate, and a great orator, very original thinker. And the presentation of the material is also very original, which has its own quirky, notations and comments, but they are valuable. And the notation, I believe, is much more logical than the historical or conventional notation we follow. So be aware of that when you're reading this book. This is not really a typical textbook, but you will learn the material nonetheless if you go through this. And then people who are looking for a bit more advanced treatment, I would recommend graduate level books. Graduate level books, of course, will require a bit more mathematical sophistication than an undergraduate level book. So these books, the first three references are the state of the art, the book by Jackson, the book by Schwinger and others. Schwinger, as most of you know, was Feynman's great collaborator, not collaborator, but more competitor, also a Nobel laureate. They split, the two of them split a Nobel Prize, along with the Japanese Tomonaga on quantum electrodynamics. And it is only fitting that each of them will have their own textbook. So this book is a bit more advanced. I won't recommend it for the faint-hearted, but yeah, it's a good book. And then there's the book by Landau and Lifshitz. This is from the Soviet school. So it's extremely terse, but it has everything which we need. So a lot of people also use this book. And then there are the classics by Panofsky and Phillips, Melvin Schwartz, and Stratton. You can also check out these books. These are advanced books. Especially people who are majoring in physics should know where to look for advanced material. Okay, so this is about references. And also, since this is a class which is being conducted in online mode, I also have some online resources recommendations. And as a caveat, I haven't gone through these. I've only got glimpses of this material, and it looks good. First one is the Nptel Courses. These are actually video lectures recorded by faculty from the Institute of Science and the various other IITs, in which the professor is giving a video lecture, and you can also see his workings on some kind of a screen, so you can see the math as well as everything. So these are very nice. So the first one which I would recommend is the one by Deepan Ghosh, who is the professor at IIT Bombay, and his introduction to electromagnetic theory is pretty nice. And then the other one is by my teacher back from the days in IIT Kanpur, Manoj Harbola. He has a set of lectures on electromagnetic theory, and the links are provided here. These lecture slides will also be available on the Google Drive folder, which I will share with you all. And you can also follow the links, or you can just Google and find out for yourself. The second resource online is the MIT Open Courseware. Of course, there are a million electromagnetic courses, electromagnetism courses. The one which I thought was roughly, covered the same, not content exactly, but yeah, similar level, I would say, is Electromagnetism 1 and Electromagnetism 2. Electromagnetism 1 is a huge course. I think it has a huge enrollment size, around 200 or perhaps even more, and hence it is taught by different instructors at different sessions. So there's no instructor, but Electromagnetism 2, I believe, is a bit more advanced level, and only a subset of people who take Electromagnetism 1 took Electromagnetism 2. There was only one session, and this course was taught by Alan Guth, who happens to be one of the greatest cosmologists who discovered inflation. So the great thing about MIT courseware, you get to learn physics from people who are Nobel laureates or the masters of their trade. So you can check out these courses if you're having difficulty and you want to learn something in detail. Please check out these courses. Although I will not strictly speaking follow them, I have my own way of doing things, because as you know, we are a fractal system, so fractal academics operates in a different way. The duration is smaller, shorter, so we can only cover a subset of topics. So this is a huge caveat. All these online resources, they are from 1 semester to 1 year long courses. So we will not be covering the content of these courses. Is not exactly the same as the content of our courses, okay? Our fractal course, which is a 1 month course. So there will be a lot of omissions. So just to clear my conscience, I will tell you what are the omissions. But before that, let me give you a rough course outline. So at the beginning, I will review some vector calculus. The reason is that although I'm aware that most of you have taken some class on multivariable calculus where you have learned a little bit of vector calculus, or maybe you've taken a physics class, I still find students to be a bit weak. Their mastery over the command over the index notation is a bit weak and they struggle. So that's why I'm going to review this. So we'll introduce a lot of notation and the algebra of Cartesian vectors. After covering algebra, we will cover the calculus of vectors. For that, we will have to introduce different differential operators. And then we'll learn about an equation of vectors. Vectors have multiple components, and of course you can integrate them in many different ways. Most of you have heard of what a line integral is, or a surface integral is, or a volume integral is. So these we will need to know when we do electrodynamics. And then there are a set of theorems associated with integration of vectors, which are also very important because they simplify calculations a lot. We will learn about them. And finally, we will move from Cartesian coordinate system to curvilinear coordinate system, such as the spherical polar coordinate system and the cylindrical polar coordinate system. And the reason being is that problems simplify a lot when you write down the problem, write down the equations in the correct coordinate system, which captures the symmetry properties of the system. Okay, so that is why we will move from Cartesian coordinates in which the coordinate axes are straight lines to curvilinear coordinates in which the coordinate axes are curved lines. Okay. However, we will consider orthogonal coordinate systems, in which although the coordinate axes are curved lines, they will intersect at 90 degrees. Okay, and I gave the two examples which we will cover: spherical polar and cylindrical polar. There are actually many more parabolic coordinate systems. We will not learn them, but the technology we will develop here will be enough to cover those cases as well. Then we will talk about static charges and static currents and the electric and magnetic fields they will produce. As you can imagine, the word static means there's no time dependence. So static charges will lead to the creation of electrostatic fields, both in vacuum and in matter. And when I say matter, in electrostatics, we classify matter into two large categories. First is conductors, and the second is dielectrics. Okay, anything which is not a conductor is a dielectric. A conductor is something which is an infinite supply of free electrons or free charges, and anything which doesn't have an infinite supply of free charges is called a dielectric. So by this classification, semiconductors are dielectrics. Okay, so any matter we will classify either as a conductor and dielectric. This is only in electrostatics. In electromagnetism, when we have dynamical fields, we will see the situation is a bit different and the classification is a bit different. Then we will talk about steady currents. As I said, steady currents are produced by charges which are moving with uniform velocity, or actually the right word is by there's nothing as uniform velocity, but the overall velocity is average velocity is uniform. And they will produce magnetic fields which do not have a time dependence. So the constant, not constant in space, but constant in time. They don't evolve in time. So they will create magnetic fields. And just like electrostatics, we will look at magnetic fields which are created by steady currents in vacuum and in matter. So these are known as paramagnetics, for which there is which get magnetized in the direction of the applied magnetic field. Then these things you've already had some idea from in high school. So here, what we're going to do mostly is use the technology of calculus to write these equations in differential, especially differential form. And then the new thing would be electrodynamics, which is the general case in which you do not consider limited kind of cases such as charges at rest or uniformly moving charges or steady currents. Instead, we will consider the most general case when the charges are going in some arbitrary velocity, some arbitrary acceleration. The current is fluctuating with time; it's not steady. And what is the general scenario? What is the general case? And the electric and magnetic field produced by such kind of sources are governed by something which is known as Maxwell's equations. I believe you have already heard of Maxwell's equations or come across it in high school, albeit in integral version. In this course, we will be looking at the differential version because we will spend some time talking about vector differential operators, this will allow us to write down Maxwell's equations in a differential version, which is much more powerful than the integral version. And then using these Maxwell equations, we will study electromagnetic waves, which is the third category, or the third character. Apart from electric and magnetic fields, we have the third character in the story, which is electromagnetic waves, or electromagnetic radiation to be precise. Electromagnetic waves will play a stellar role in this course. They are the third important character. We'll look at electromagnetic waves in vacuum, in media, and a variety of phenomena associated with electromagnetic waves, which you've already encountered as optical phenomena, for example, reflection, refraction, absorption, and dispersion. Okay, and then we will also consider waveguides, which is the science behind the electrical or EM wave communication, right? EM wave signals are transmitted to wires or cavities or guides. So we will study the physics of that using Maxwell's equations. As I said, it is a 1-month course. That means we are going to have to sacrifice some of the material. So let's look at the items which are going to be conspicuous by omission. First item is boundary value problems. Boundary value problems form the heart of electrostatics. However, we will not cover them. So we will learn about what the equations describing the EM electrostatic field are. We will just not solve the equations for the general cases, okay? So this will require solving Laplace or Poisson equation. People who have taken partial differential equations will know a little bit of what I'm talking about. So Laplace or Poisson equation, there are a set of whole bag of tricks which have been around since, I would say, 2 centuries, because electrodynamics is a pretty old and established subject. These are the method of images, separation of variables method, Green's function method, and then of course there are computer-based numerical approaches which are also very powerful. Unfortunately, none of which will be covered in this course. Okay, so for this you have to wait for a more advanced level, junior level course in electrostatics or electrodynamics from the Department of Physics. Those of you who are interested should enroll in that course. And then multipole expansions, another important thing, but we will cover it only partially. Another important omission would be DC and AC circuits. Most of you have some idea of this from your high school. In fact, I would say there's a bit of a saturation of this material. We will not need to know about circuits in this course. We will omit it, RC circuits and all that, LCR circuits. Another important omission, which is very close to my heart, is the special relativistic formulation for electrodynamics, including space-time tensor notation. And the reason I feel this is important, because electrodynamics, in effect, led to or pointed us to the direction of a much more deeper structure of space-time, right? And from electrodynamics is Einstein fashioned this special theory of relativity, which changed the concepts of space and time, that they must be welded together into a single dynamical entity, which is space-time. All that intuition came from electrodynamics. So I would say that was the principal goal. After that, I think this is the most important contribution of electrodynamics to the thought of humankind, was the idea that it revealed the deeper structure of space-time. But we will not have time to cover all this. Again, you have to wait for a class in classical field theory or advanced course in electrodynamics to come across these. And then radiation, we will have to leave out a lot of topics. Radiation from accelerating charges. Radiation theory in general we will cover in a sketchy manner. I will only cover the important stuff, but there are other things which we need to cover at some point, which we will not have time, actually, we will not cover. For example, Cherenkov radiation, synchrotron radiation, these we will not cover. And I mean, unless of course we have some time. But from my past few years experience, we are always short of time in this course, so let's forget about this. A little bit about the evaluation plan or the grading. So the assessment will be based on a final exam of 100 points and 3-hour duration. In addition, there'll be 3 or 4 online quizzes. Each quiz will be I have to figure this out. I haven't yet figured out how to conduct the quiz online through Google Classroom, but I'll do that shortly. At the end of this week, there'll be a quiz. So each quiz will be 10 points and 10 minutes duration. So this is, grading is absolute important thing. There's no relative grading in this course. So you score an A, you get an A only when you score in excess of 80. Okay, not 80. You have to score between 81 and 100 to get an A. Of course, if you get somewhere between 71 and 80, you get A minus. If you score somewhere in between 61 and 70, you get a B, so on and so forth. You can work it out yourself. A tentative final in review of grades, the timeline for this is July 2020, but given the pandemic, I don't know when the school is going to be back in session. So the idea is whenever the school is back in session, we will have this final exam, which is a 3-year exam. This is the plan, but most of us know plans in this day and age is a bit of a, unsure thing. So we will have to wait what happens in the final. But the final is going to be a 3-hour exam, 100 points. I will also post some assignments which will not be evaluated. This is for you because I don't have access to the TAs during this time. So there'll be no evaluation of the assignments, but they'll be for your practice, and I'll put them up in any case so that you can have an idea of what kind of questions you're supposed to face in the final. Okay, with all that introduction, let's get to the meat of the course. We'll start with the review of Cartesian vectors. As I said, I will review some notation and some terminology. We start with the age-old question, what is a vector? I think most of you have learned this in high school. A vector is something which is a directed line segment, something a quantity which has both a magnitude and direction. This is given by this directed line segment. This is an example of a vector. It has a length, which is the magnitude, and of course it has a direction pointed out by the arrow. An example, so you must have heard this phrase in high school, which is the directed line segment. This is what a vector is, and one example of this is the position vector. So let's consider this object P, which is located somewhere in space. If we set up a coordinate axis system, x, y, z, with the origin O, the position vector is the vector joining the origin to the point P. So the magnitude is, of course, going to be the length of the vector, the length of this arrow, and of course, the direction from O to P gives you the direction of the vector. We'll come back to this figure later when we're talking about components. But basically, you can draw perpendicular from P to the x-axis, to the x-axis, to the z-axis, and the y-axis. And the length of the intercept where the perpendicular is drawn will give you the corresponding component. We'll come back to this figure later. So what is a vector? A simple answer will be quantity. A vector is a quantity with both magnitude and direction. The directed line segment, and the example is the position vector. However, in this course, we are going to take a much more sophisticated view of a vector, and we will introduce a different definition, which is a bit more less ambiguous and more specific. Vector is a position, something which behaves. A vector is something quantity which behaves like position vector under vector addition and multiplication by a scalar, and it also behaves like a position vector under rotation of coordinate axis. Okay, so what I am trying to say is that if we take this coordinate axis and if I rotate this coordinate axis, the origin remains fixed. You rotate it around the origin, then this vector, components of this vector OP will change in a particular kind of way, a very specific kind of way. A general vector would be something which should mimic that kind of transformation. Okay. So before we look at general vector, let's study position vector a little closely. A position vector, most of you are familiar from high school, is a 3-component object or a triplet, giving the location from an origin of coordinate system. So usually it is given either by a row vector or a column vector, x, y, z, these components. As I said, the way to get these components is to start from the tip of the vector and draw perpendiculars on the x and y and z axis, and the length of the intercept where the perpendicular drops on the axis, it gives you the corresponding component. So if you drop a perpendicular from P to the z axis, the length of the intercept will give you the length of the intercept on the z axis will give you the z component. Okay. We will switch to a different notation in which instead of x, y, and z, we will use x1, x2, and x3. So x with subscript 1, subscript 2, and subscript 3. And the reason is twofold. First, of course, we want to generalize from 3 to higher dimensions, 3, 4, 5. So then, but we will run out of letters in the alphabet because it concludes at z. So we don't want to, we want an inexhaustible list. An inexhaustible list is formed when you use natural numbers 1, 2, 3, and so on to infinity, as many dimensions you want. And the other thing is because we want to use an index notation in which this 1, 2, 3 are going to be replaced by Latin indices, so in an abstract form, which will simplify calculations a lot. So let's look at the notation, the component notation, in which the vector components, instead of x1, x2, x3, will be given by x subscript k. X subscript k, k can take values 1, 2, or 3. The entire vector, instead of this triplet, instead of this column vector, I will denote it by a boldface or with an arrow overhead. Okay, in my slide it will mostly be boldface. When you are writing your exam or doing homework, you should always use the vector, the arrow overhead, or just use a bar. But don't just leave it like that without an arrowhead or a bar. Then you lose points, as some people do in the final. They're sloppy with the notation. If you're sloppy, then as a grader, I won't be able to tell whether you're talking about a vector quantity or a scalar, and then you get points deducted for that. So, as I said, let's look at the rule of addition for vectors. Most of you have learned the parallelogram law in high school. It's complicated. I think a better way of approaching vector addition is by addition of components. So we have two vectors x and y, and these have components x1, x2, x3, y1, y2, y3. The vector sum of these two vectors is given, this triple equal to means defined to be. So the vector sum is defined to be just the sum of the respective components. Okay, so this vector sum is a new vector which has components whose which is algebraic sum of the individual respective components of x and y. It's very simple. If you use instead something which is known as the parallelogram law, it looks very, it has sine theta, cos theta, and all that kind of complicated stuff. Simple way to introduce is this in terms of components. And then, of course, there is vector multiplication by a number or a scalar, lambda. So, so lambda is a number. It could be 1.3, or it could be cos theta, or anything. So if you multiply a vector by a scalar multiple or a number lambda, all you do is you multiply individual components by the same number lambda. Okay. So lambda of x is equal to lambda x1, lambda x2, lambda x3. Okay, very simple. Now, once we choose the vector to be a column, which we are doing in this course, the row vector, we will use the transpose. Okay, the row vector is the transpose. So when I denote x, I denote the column vector. When I write x transpose, what I mean is the row vector. Again, very simple, just to be clear. We also introduce the notion of a basis. These components, x1, x2, x3, we can write this vector just from what we learned about vector sum and vector multiplication from these two information. We can show that you can write this as x1, x2, x3 is equal to this vector sum of three vectors, x1 times 1, 0, 0, plus x2 times 0, 1, 0, plus x3 times 0, 0, 1, right? So you can check by the rules of vector addition and multiplication stated before that indeed this sum is equal to this. Now this special vector 1, 0, 0, 0, 1, 0, and 0, 0, 1, the set of three special vectors are formed something which is known as a basis, in which we can resolve all vectors. So this can be done for arbitrary vectors, right? You can take the first component times the second component times this component tells you which different vector it is. But these remain the same for all vectors, right? The basis remains the same. The coefficient changes. This coefficient, basis expansion coefficient changes. So x1 times this, if we call this vector as e1 hat, so this is equal to x1 times e1 hat. This is equal to x2 times this vector is e2 hat. So this is x2 times e2 hat, and then x3 times the 0, 0, 1, which we're calling x3 hat. So this is x3 times e3 hat, right? And then we can use the component notation. As I said, when you in the component notation, you change you instead of using 1, 2, 3, you use the label xk. So xk, and then e must have the same label, so e hat k, and then we sum k over 1, 2, and 3. X, because 1 will correspond to this term, 2 will correspond to this, and 3 will correspond to that. So in component notation, the same vector x can be written as in the basis, with the basic expansion coefficient being the components. Okay. After addition, we learn multiplication. As I said, multiplication, we can define several products. We have already defined a product of a vector with a Reynolds number or a scalar, but here we are considering a product of two vectors. Okay, so there are many ways to define a product of two vectors. The first one which we encounter is something which is known as the dot product. Actually, this is not the first time you're encountering. You probably know this from high school. So review. So x dot y. That's why it's called a dot product. Sometimes also known as the inner product or a scalar product, because it's called the scalar product because the result of this is a number. It loses the vector property, right? So x dot y, this is defined to be the row vector x times the column vector y. Okay, row vector times column vector. Most of you know how to multiply matrices, so you can perform this multiplication, row vector times the column vector, and you'll get this answer, x1 y1 plus x2 y2 plus x3 y3. So again, we can write this in a nice compact form using indices, Latin indices, xk, and y must also have the same index, so yk, and then k goes over 1, 2, and 3. Okay, so this is the compact way of writing. So one thing you notice is this huge summation sign, which looks pretty ugly, and we have to do something about it. And Einstein actually did something about it. He introduced the Summation Convention, which cleans up the notation even more by eradicating this summation sign. Okay, what he gave is a set of rules which constitute this Summation Convention. It should be called Summation Conventions, but anyway. Rule 1 is that any index which is repeated is to be summed over all values, 1, 2, and 3. For example, the x vector we wrote in terms of resolved in terms of components. It was this component xi times the ei hat basis, and then sum over all the elements of the basis. Now, because I is already repeated, we don't need to put Einstein recommends that you get rid of the summation sign. So this is just xi ei hat. The fact that this is I is repeated already implies there is a summation. Okay. Similarly, the dot product, which we found to be xi yi sum over I goes from 1 to 3. Because I is repeated, we can forget about the summation symbol because automatically it is implied. And the second rule is that indices which are not repeated, they're free. They don't have to be summed over everything. They can take any value which we choose. Like we can give them value 1 at a time, or 2, could be 3, but not all 3 at the same time. Okay. On the other hand, I has to be summed over anything which is repeated has to be summed over all values 1, 2, and 3. Then there are a couple of associated subrules. First is that the repeated index cannot appear more than twice. Okay, it cannot appear more than twice. For example, I have an illegal expression xk, xk, yk. Now k, the index k has appeared 3 times, so this is illegal. In fact, this is illegal not because of just some random rule, because this is inconsistent. It gives you wrong results. So if you proceed with this expression, it will give you wrong conclusions with the problem. So in the Google Drive, I will drop note in which you can see why, if you repeat an index more than once, it leads you to incorrect conclusions. A lot of people in the exercises make mistakes or in the final make mistake because they repeated an index. Please don't repeat this. Repeat an index more than 2 times. That should immediately give you a red flag that there is something wrong. If by accident you encounter during your calculation that you have 3 or 4 times repeated an index, it means there is something wrong and you have to trace the mistake. Finally, there is a sub rule is that a repeated index can be relabeled anytime. So it's a dummy index. And this is analogous to the situation in single variable calculus when you have a definite integral. The definite integral, the integration variable can be anything. It can be x or y or z, right? Because it at the end of the day, it gets integrated out, and you only have the limits of integration which enters in the final expression, right? So that's why repeated index, just like the integration variable for a definite integral, has no individual meaning of its own. You can relabel it anytime. It has a meaning. I'm sorry. It doesn't have a it can be relabeled anytime. So repeated index, and you can find often expressions in which the left hand side will have many repeated indices, and the right hand side will not have any repeated indices. But the free indices on both sides of an expression should match. Okay, this is how you know your algebra is correct. Is if you have an equation in which both sides have the same number of free indices or the same set of free indices, but they can have differing set of dummy indices. Okay, so dummy indices you can relabel anytime. Let's move on to define something which is known as the norm, or the size of a vector. It's given by this notation with the double bar on both sides. And this is defined to be the square root of the self dot product. So you take the dot product of a vector with itself, and then you take the square root. In component notation, this looks like xk, square root of that, okay? As I said, we can define different kind of product of two vectors. The second kind of product of two vectors is something which is known as an outer product or a tensor product of two vectors x and y. In fact, this is not a single object, but there are actually 9 objects. The outer product consists of 9 objects. So outer product TLK is the product of the lth component of the x vector and the kth component of the y vector. Okay, and you can also guess, or you can also probably figure out that this is not a symmetric product, unlike the vector dot product. I'm sorry. So this, as I said, outer product consists of many components or many entries, and all of them can be stacked together nicely in a matrix, which is denoted by this double-headed arrow T or bold-face T. So, and the idea is that the ijth component of this will give you the product TIK, which is xi yk, right? So 1 component of this will give you x1 y1, and 1 2 component will give you x1 y2, so on and so forth. Clearly, this is not the same as YL XK. That is, so the ordering matters when you have an outer product. Most of you who have taken a class in classical mechanics already know, come across the outer product when they're doing rotational mechanics. Most of you are familiar with something which is known as the moment of inertia tensor. Moment of inertia tensor has such kind of outer products. Okay, so in physics they are also common. The third kind of product which we are interested in is something which is known as a vector product or a cross product. Now, I want to emphasize that this vector product cannot be always defined. By always, I mean not in all dimensions. For example, in 2 dimensions, 2 by 2 vectors, you cannot define a cross product. Okay. In 4 dimensions or 5 dimensions, you cannot define a cross product. So this is very special to 3 dimensions. On the other hand, the outer product and the inner product or the dot product, they can be defined in all dimensions. How do we define the cross product of 2 vectors, x cross y? This you've already learned in high school. You had some kind of matrix in which you had defined the cross product, right? You had a matrix. However, we're not going to do matrices because we're interested in compact expressions with indices. So the way you define it in this way, so x cross y, as the name suggests, the result of this product of two vectors is going to be another vector. So if it's another vector, it can be expanded in a basis. So this is the basis element, xk, and this is the basis expansion coefficient. So the basic expansion coefficient knows that it's a product of x and y, so that's why it's made up of x and y. And the kth component of this, that is the companion of the coefficient of ek, is whatever the kth component. The kth component is given by epsilon ijk, xi, yj. So it's a product of three things. These are all the numbers because they're components. Epsilon ijk, xi, yj. You can see I and j are repeated, so that means they get summed over. They don't have their own existence after that, after they get summed over, and only k is left over. So that makes sense because this is the kth component of something. Epsilon ijk is something which is known as the Levi-Civita symbol. Some people call it the Levi-Civita tensor, or the completely antisymmetric symbol. The idea is that this guy, epsilon ijk, is completely antisymmetric under swap of any two of them. So if you swap I and j, it will become a minus sign. If you do odd even number of swaps, it will be a plus sign because, minus 1 for each swap. So if you have even number of swaps, minus 1 raised to the even power gives you positive quantity. And the way we define this is that if you have cyclic permutation of 1, 2, and 3 in the indices, I, j, and k, then you get a plus sign. If you have anticyclic permutation, it will have minus sign because anticyclic permutation can be obtained from the cyclic by odd number of swaps of indices. And finally, if you repeat an index, if I, j, k, if some index is repeated like 1 and 1, all this is 0. This is true by antisymmetry, right? By antisymmetry, if you swap 1 and 1, you do an odd number of swaps, so you pick up a minus 1, but the thing doesn't change. So there's only one quantity which is negative of itself, which is 0. That's why if you have an index, same value for the index, then Levi-Civita for that component for that combination is 0. Okay. So in terms of the Levi-Civita, I've written down the component of the vector product in terms of the vectors which are undergoing the product. Okay. So let's check. It gives you what you had learned about the cross product in high school. Let's compute in particular the first component. Okay, the first component of this. First component means E1, the component which is accompanying E1. So K is 1. So K is 1. Let's go. K is 1. And Ij is, as I said, it's a dummy index, it's a repeated index. So the first component is given by this expression. Now I and j are both repeated, so we need to sum over all values of I and j. To simplify, we first sum over I, and then we will sum over j. So sum over I appears in the epsilon and in the x. So I will be 1, and then I will be 2 in this term, and then I will be 3. So epsilon 3 and x3, right? But 1, the first term has two 1s appearing in the epsilon, so this will be 0. These two are non-zero, so this is what is the answer. Now we sum over all the j's. So the j, it can take value 1, it can take value 2, and it can take value 3. But the moment it takes values 1 and 2, this will be 0 because epsilon is completely antisymmetric, so it has taken value 0. And then the only non-vanishing case is when this j is equal to 3, I'm sorry. So this j equal to 3, so y will be 3. So the first term is x2, y3. Similarly, you can show that the second term is minus x3, y2. You can just do it by yourself. So it's 3 and 1, so j can only take value 2. For the other cases, it is 0. So 3, 2, 1, x3, y1. And 3, 2, 1 is an anticyclic permutation of 1, 2, 3, so that's why the minus sign. Okay. So what we have derived is that this first component is the sum of these two, but then these two are x2, y3 minus x3, y2. Now this is already familiar to you from high school when you did the cross product using matrices, using a 3 by 3 matrix. Remember how to take cross product using a matrix. mind yourself, and you should be satisfied that indeed this is the case, which we learned in high school. Okay, so the algebra part is complete. As I said, if we go back a little bit, I said that behaves like position vector under vector addition and multiplication by a scalar. We have discussed these two. What remains to be done is transformation under rotation of coordinate axis. Okay, so let's do this. So as a warm-up, we will consider this two-dimensional situation. How does the components of a vector change, two-dimensional vector, which is a doublet, under rotation of coordinate axis. Okay, so here's the situation, what we are talking about. We had an x and y coordinate system, which is the orthogonal Cartesian coordinate system. And then I rotated the coordinate system by an angle theta. So x goes to x prime axis, and y goes to y prime axis. Okay, OP again is the position vector of the point. Position vector. It is clear from the diagram that the components will change. For example, the components are, as I said, you drop a perpendicular from P to the x-axis, and then the length of the intercept, OA, gives you the component. This is clearly different for the new x coordinate, x component, because if you drop a perpendicular from P to the new x-axis, the length of this x prime is very different from OA. So OM is different from OA. This is what I'm trying to say. It is clear that it will change, but it will change in a very precise manner. You can work out by trigonometry, as you have done already in high school, is that the component change according to this rule. The new x component, x prime, is equal to x cos theta plus y sin theta, and y prime is minus x sin theta plus y cos theta. So this set of equations shows you that first thing is that this is a linear equation in x and y, linear homogeneous equation. And most of you know linear homogeneous equations can be rewritten as a matrix equation. So matrix equation x prime y prime is equal to this matrix multiplied by xy. So further, more compactly, we can use the notation in which this is the two-dimensional vector x prime, this is the vector x, and this 2 by 2 matrix is this quantity O, which is the tensor, 2 by 2 tensor. So in this way, we have written this equation in this very compact form. You can identify which these quantities are. Now, one curious thing to check is that this rotation matrix, this rotation which has been represented as a matrix multiplication, with O being the rotation matrix, is an orthogonal matrix. You can work out O transpose O, and the matrix product will give you identity. Right? And let me remind you what an orthogonal matrix is. Already, although I guess most of you know, something which has its own transpose as its inverse is an orthogonal matrix. And this pattern will persist when we go to higher dimensions. In three-dimensional space, rotations of coordinate axes are given by an orthogonal matrix, which is a 3 by 3 matrix. So the same equation, x prime equals O theta of x, except instead of one angle, there'll be three angles, which are the Euler angles. So, but the equation will remain the same. It will be a linear equation, and it will be an orthogonal transformation. So, new components can be obtained from x by doing an orthogonal transformation. So, you can write this equation in a component form. So, x prime has three components. So, we can consider the ith component of x prime, which is x prime I. And then using the matrix multiplication rule and the Einstein Summation Convention, this is equal to Oij xj, right? This you know from high school, how to define matrix products. Then this is just an expanded version of this. O11, O12, O13 are the components, and then these are the components. So it raises the question, why is it that rotation matrices are orthogonal, right? Why should coordinate axis rotations be given by orthogonal transformation? And the reason is because rotations preserve the length. So under rotations, length or norm of a vector remain the same. So this self-dot product, this remains the same. In fact, what you can show is that the dot product of two arbitrary vectors doesn't have to be itself, but in general, x dot y, that is preserved. But nonetheless, this is more intuitively clear when we look at the diagram, is that the components x and y have changed, right? So x and y have changed to x prime and y prime. But the length of the vector, which is the distance from the origin, that doesn't change under the rotations about the origin, right? Because it is anchored at the origin, its length didn't change. So the length doesn't change. And now let's rewrite the left-hand side of this equation a little bit. So x prime dot product, as I said, in the matrix version, it is given by a transpose times x, the column vector. So, and also rotations, as I said, rotation, the prime is equal to O times x. So the prime is equal to O times x, and the prime is O times x, but then you have to take a transpose of that, which will reverse the order. So when you take the transpose, OX transpose is X transpose O transpose, multiplied by OX. So you have X transpose X, and O transpose O, which is in between. So you have O transpose O sandwiched between X transpose X. So if I plug this in this equation becomes the second line, X transpose times O transpose O times X is equal to X transpose X. Now these two sides can only be equal if this quantity inside is equal to the identity matrix. But then, if you look carefully, this equation is just the defining equation of an orthogonal matrix, right? O transpose O equals identity. This is the definition of an orthogonal matrix. So that's why rotations, because they preserve lengths, they must be orthogonal transformations. Now this equation 1, you can also write in component form. This is index component free form. There are no IJKs hanging around. This is a good form to look, but to do manipulation, the index form is better. So the index component notation is OIJ, OIK equals delta JK, right? So I introduce a new quantity, this delta JK, and we will see momentarily what this is, but this is a nice way of writing the component form of equation 1. So let's see how do we get this? So component notation, ijth element of the matrix O, most of us are clear that this is given by OIJ. The element of the transpose, that is O transpose Ij, will just be given by the row and column entry swapped. So O transpose Ij is equal to OJI. Component of the identity matrix is given by this symbol, which is known as Kronecker delta, okay, delta Ij. So identity matrix ijth component is given by delta Ij. So what is the definition of delta Ij? They have the following defining property. First is symmetry. So delta Ij equals delta Ji, and delta Ij is 0 if I and J are non-zero. Okay, I and J are not the same. If I not equal to J, then delta Ij is 0. So delta 1, 2 is 0, delta 2, 3 is 0, delta 3, 2 is also 0, and delta 1, 3 is also 0. So whenever I and J take different values, the Kronecker delta immediately becomes 0. Kronecker delta is non-zero and equal to 1 when I is equal to J. So delta 1, 1 is equal to 1, delta 2, 2 equals 1, and delta 3, 3 also equals 1, right? So you can check that indeed, with these defining properties, the component of the identity matrix is equal to delta Ij. So for example, I11 we know is 1, and delta 11 is also by this rule is equal to 1. I10, 13 we know is 0, and delta 13 is also 0, so on and so forth. Okay. So we introduce the Kronecker delta to denote the components of the identity matrix. Now, let's go back a bit. So we have this equation, O transpose O equals I. Let's take the JK component of both sides of this equation, okay? So O transpose O, JK component, and this is also a matrix, so take the JK component of this. So JK component, or JK element, I'm sorry. So identity matrix, we just saw, in order to write this, we need to write this equal to delta JK, right? Identity jkth element of the identity matrix is the Kronecker Delta symbol jk, and O transpose O is the matrix product. So we know how to take matrix components, component form of a matrix product. It will be ji, and ik, right? The middle index should be the same, and then there's sum over I, but we don't need to denote that because we are using Einstein's summation convention. So O transpose ji, O ik, this is the jkth element of this product. And then, because this is a transpose, this should be equal to the row and indices will get switched. So it will be Oij instead of O transpose Ji. So we have Oij, Oik equals delta Jk. This is exactly what we had in the last slide, okay? This is exactly what we had in the last slide. So we have established this in the component form, the orthogonality condition in the component form, which we will use many times over in the course. So that's why I went through the pains of, literally going through every step of it so that you get it once and for all. So I think this is a good point to stop. It's close to 1 hour. So let me do a quick summary of what we did in this lecture. First, we introduced indices for components of a vector, something which you are probably already familiar, but it's nice to review. And then, important thing is we introduce Einstein Summation conventions for indexed objects to clean up notation. So no more summation signs. Only 2 kinds of indices. They can be either dummy indices or free indices. Okay. And we have seen how to simplify dot products and cross products using summation conventions. In particular, for the cross product, you don't have to write a huge 3x3 matrix. Instead, you write it as one compact expression. More importantly, we introduced 2 new symbols. While using the defining the cross product, we introduced the Levi-Civita antisymmetric symbol epsilon ijk, which is completely antisymmetric. And then we define the Kronecker delta, which is symmetric in its components I and j. So this is delta ij. And finally, we reviewed how rotation of coordinate axis is accomplished through orthogonal transformations on the position vector, not just any average wave vector. But yeah, in the next lecture we will see that this is how we will also define general vector, not just position vector, through its properties under rotation of coordinate axis. Okay, how its components will change. We will define a vector to be an object whose component will change in identical fashion to that of the position vector under rotation of coordinate axis. That is going to be a new definition or new and improved definition of a vector. Okay, so at this point I would like to stop. Please send me emails if you have queries. I will make these lecture slides available on the Google Drive, which I'm going to share with all of you. And yeah, there are some other folders. You can check out the differences. You can check out the assignment folder, although I don't have anything there right now. In a day or 2 I will. Okay, till next time we meet, which is actually we don't meeting, but I will make the lectures available one by one in particular dates which we will have the classes. Today at 9 o'clock there was a class. There's supposed to be a class, so this is the lecture for that first class. Okay, so I will stop here. Thank you.